Hello everyone. In my first video, I explained why we need modulation in the communication system. And also I explained different types of modulation techniques like analog modulation, digital modulation. Now, in this video, we are going to study about first method of analog modulation technique, which is commonly used in the 80s and 90s and early 2000, we can say, and that method is called amplitude modulation. Okay, so what I'm going to explain in the video is definition of amplitude modulation, and then how to represent the AM wave in the time domain and in the frequency domain. So this is my topic for this video. I welcome all for this discussion. Now, see, in this slide, what I have shown here is how the modulation process takes place and demodulation process takes place, and how do you represent the signal or the waveform in the time domain. Now just see here, I have a modulator as well as demodulator. A modulator is used to represent a baseband signal or the original signal. What I have shown here, let us say this is my original signal. This is my original signal, and this is my original signal here. This is my original signal, I can say. So this original signal is actually represented in a cosine wave, we can say a cosine form. It's having a frequency of, say, FM. The frequency of the signal is FM. It's a message signal or a baseband signal or a low pass signal. I call this as low pass signal because all the message signals will be a low frequency signals. That means it will extend between, say, audio band, if I consider, it extends between 20 Hz to 20 kHz. Or if I consider a voice band, in that case, the frequency is between 300 to 3000, 3400, or roughly 3000 Hz, practically taken as 3400 Hz. So most of the signals are low pass. A baseband, original signal, message signal, or we call them as a modulating signal. So I apply this modulating signal to the modulator. For modulator, we also apply a high frequency carrier, which after modulation, that's what we get, the AM signal. So this is a carrier signal, a band pass kind of signal, not low pass. It's a band pass type of signal with a frequency of FC, okay, where that FC is very much higher than FM, the frequency of the message signal. And here, just look at this, the amplitude of the signal is continuously changing. It is changing proportional to the amplitude of the message signal. This is the message signal, right? According to the very envelope of the message signal, the amplitude of the carrier is changing. That's what we get a AM signal. It is transmitted over a channel, and in the receiver, we use a demodulator, which is used to convert this signal back into the original form. The original signal is your message signal with a frequency of FM Hertz. So usually the frequency of this carrier is very much higher. If I take an example of the GSM cell phone, global system for mobile, a cell phone frequencies, it works under 900 and 1800 megahertz band, basically. So those frequencies are nothing but they are the frequencies of the carrier signal. Now, we will move to the time domain representation of a AM signal. So how we represent mathematically in the time domain, that is time versus amplitude, what we say in the waveform method, if I represent by using a waveform, how to get that equation in the time domain. Later I will explain how to represent in the frequency domain. Now, what is amplitude modulation is? The amplitude modulation is nothing but it is the process of changing the amplitude of the carrier signal, okay, linearly with respect to whatever the variation which is happening in the message signal amplitude, the instantaneous amplitude, what we say. As the instantaneous amplitude of the message signal changes, we have to change in the modulator, we have to change the amplitude of the carrier signal proportionately, as I showed earlier in the waveform. Okay, now to get the equation for the standard equation for AM, let us start with assuming that I have a carrier signal which is mathematically defined with this particular equation, that is C of t is equal to AC cos 2 pi FCT plus phi C. I have not considered the phase part here because the phase and the frequency are kept constant. Only the amplitude of this particular carrier, that is the peak, this is AC is a peak amplitude, where this amplitude of the carrier signal is varied according to the amplitude of the message signal. Now, let us again consider one more signal, that is a message signal or information bearing signal. That means it's an information signal or a message signal or a low pass signal, which is represented by m of t is equal to a m cos 2 pi fm t. Fine, this is our message signal, this is the carrier signal. Now we'll start with assuming that I have a standard AM equation Okay, a amplitude modulated signal which is represented in the time domain is a standard equation which is given by AC into 1 plus Ka m of t cos 2 pi fct, where this Ka is nothing but it is the amplitude sensitivity parameter of AM. It's a sensitivity parameter, amplitude sensitivity parameter Km, Ka multiplied by the message signal. Now just look at this signal here, standard equation. The signal is nothing but it is AC cos 2 pi fct, which is your original carrier, and this part is nothing but the amplitude part of this particular signal with the frequency of fc. So this amplitude term, this particular term actually varies or changes. This is what we need to do in the amplitude modulation for a carrier. So this amplitude part is going to change proportional to the instantaneous amplitude of the message signal. So as instantaneous amplitude of the message signal changes, this entire envelope, what we say AC into 1 plus Ka m of t is nothing but it is the envelope of the modulated signal. So this is going to change. As m of t changes, this amplitude changes. We are going to retain the same frequency of the carrier. That's what we get a standard equation for AM signal. Now, in this standard equation of the AM signal, what I will do is, in the place of m of t, I will substitute this this particular component. That is, m of t is equal to am cos 2 pi fmt is substituted over here. So what I'll get this particular equation. That is, I replaced that m of t by am cos 2 pi fmt. Okay. Now I will consider this particular term, that is Ka, the amplitude sensitivity parameter, multiplied by the peak amplitude of the message signal Ka am as mu, where mu is nothing but it is the modulation index or depth of modulation in case of amplitude modulation. So mu represents actually the index, or it is an index for modulation. It actually indicates the modulation or the variation or the change which is happening in the amplitude of the carrier signal proportional to the amplitude, instantaneous amplitude of the message signal. Fine. Next, in the next, what I'll do is I multiply this term AC with this particular term. I'll expand it. I will expand this term. So what I'll get a AC cos 2 pi fct. Second term over here is Ka am AC cos 2 pi fmt fc cos 2 pi fct. That's what I have, and I have replaced that Ka am by mu over here. Okay, so I get two terms. Okay, now I will use a standard trigonometric relationship cos A cos B, which is given by half of cos of A minus B plus cos of A plus B. I will apply over here. So I get the first term which is as it is. By applying the trigonometric rule, I will get this particular term, that is mu into AC by 2, this 2, cos of 2 pi fc plus fm of t. I take this as A, this as B in this standard equation. So it's cos 2 pi fc plus fm of t plus mu AC by 2 cos of 2 pi fc minus fm of t. So the standard equation is represented in another way like this. So what exactly it indicates is what we have here is, see this. The first term, which is called as, this particular term is actually called as unmodulated carrier. So this carrier is same as this equation, right? So in the modulated wave, this is the modulated AM signal. In that modulated wave, it consists of three components. This is the first component, this is second signal, this is the third component. The first component is nothing but it is the unmodulated carrier. We call this as unmodulated carrier because this is nothing but this is the original carrier signal. We don't have any index for modulation, that is mu over here. So let's see the second case. It is mu AC by 2 cos 2 pi fc plus fm of t, right? I call this as a upper sideband. I call this as a lower sideband. So this upper sideband, the second component, has a frequency. This is a cos signal which is having the frequency of fc plus fm. Frequency is increased by fc here, or you can say the frequency fc plus fm. That's what I'll get with the amplitude equal to mu AC by 2. This is the amplitude. What about this? This is the lower sideband. So this is having a frequency of fc minus fm with the same amplitude as the upper sideband. So I have three components over here which is given by, one is unmodulated carrier, upper sideband, and the lower sideband. So this unmodulated carrier is of no use actually in this modulated signal. We can suppress it. We can remove that particular component before transmission. And here also, just look at this term, both having the same amplitude. So they are representing it consists of a mu also. Both are considering having the same amplitude. That means instead of transmitting both the upper sideband as well as the lower sideband, we can eliminate one of the sideband and transmit only one sideband. Such methods are called single sideband transmission. Fine. If you transmit only one sideband by suppressing the other sideband and the carrier, we call that method as single sideband in case of AM. Okay. So here, now moving on to the next case, just look at this representation. This is the time domain equation we know already. This is the time domain equation. This is basically a time domain equation. This is the time domain equation over here. Okay. This is the graphical representation of the modulated signal. I have taken two examples over here, two waveforms I have taken. This is perfect modulation. This is not a perfect modulation. We call this as a over modulation. So why exactly we get over modulation, or how to avoid the over modulation in the AM, that is amplitude modulation? See, we have to satisfy actually two conditions. If you want to get a perfect modulation without any distortion, phase reversals or whatever, we have to satisfy two conditions. What are those conditions? The conditions are, we have the amplitude Ka m of t, that is this Ka m of t, the magnitude of this particular amplitude here should be always less than 1. Okay, and the second condition what we need to satisfy is the carrier frequency always should be very much greater than the highest frequency in the message spectrum. That is, when I say 20 Hz to 20 kilohertz, 20 kilohertz is the highest frequency in the audio band. Or if I take an example of a voice band, that is 300 to 3000 Hz, 3000 Hz is the highest frequency, or maybe 3.4 kilohertz, let us say, no problem, no issues with that. Okay, so we have to satisfy these two conditions. Now, in case if this Ka m of t is not less than 1 but it is more than 1, what happens is here we get a over modulation, or we get a over modulation when the amplitude of the message signal, that is AM, if it is more than the amplitude of the carrier signal, that is AM is more than AC, in that case we get a modulation index which is more than 1. It is not 100% modulation but more than 100% modulation. It is not below 100% modulation. Okay, that happens when this Ka m of t is more than 1. If Ka m of t, the magnitude of Ka m of t is less than 1, we get a perfect modulation which is called as under modulation. If Ka m of t is equal to 1, or if mu is equal to 1, we call this as 100% modulation. If mu is more than 1, we get over modulation where there is a possibility of distortion. So we need to avoid this. That means the highest value what we can have for a modulation index is equal to 1. So this is about time domain representation of the AM signal. Now we will go to the frequency domain representation. I'll start with the equation again. What is the standard equation for AM in the frequency domain? Then I'll represent that by using the frequency spectrums. Now just look at this. See how to translate from time domain into frequency domain. We have to apply just a Fourier transform. That's it. So we have to apply a Fourier transform to a time domain equation, then we get equation in the frequency domain. So this is the frequency domain equation here, S of F is the frequency domain. Okay, so let us start with my message signal again, M of t. If I take a Fourier transform to M of t, that will be represented as simply M of F. Notation, that's it. Okay, where this M of F is represented, it is the message spectrum. It is the original message spectrum. Now again I will take a standard equation for AM here, that is S of t is equal to, this is also called a conventional AM equation or a standard equation. Yes, S of t is equal to AC into 1 plus Ka m of t cos 2 pi FCT. I multiply directly over here, I expand it. What I will get? I will get AC cos 2 pi FCT first term plus AC into Ka m of t cos 2 pi FCT. Right? So what I do is I apply a Fourier transform to those two terms. So AC cos 2 pi FCT. So cos 2 pi FCT mathematically in the form of exponential term I can represent something like this. This is the mathematical representation by using a Euler's rule at all. We can apply and we can represent like this. Now if I take a Fourier transform to this any exponential term, when I take a Fourier transform it will be a delta function, right? So it is AC by 2, this 2 into this term exponential j 2 pi FCT is represented as delta of F minus Fc. That is a delta function shifted by a frequency of Fc plus exponential minus j 2 pi FCT. The Fourier transform of that is delta of F minus of minus Fc which is plus Fc. That's what I'll get. So I get a delta of F minus Fc plus delta of F plus Fc. That is from the first term of this equation. That is AC into 1 into cos 2 pi fct. What about second term? We have a second term as AC into Ka m of t cos 2 pi fct, right? Isn't it? So that is Ka AC by 2 is the term. Now just look at this. I have a m of t multiplied by cos 2 pi fct. That's what I had in the second part. So m of t into cos 2 pi fct, any particular signal multiplied by an exponential term is equivalent to, in the frequency domain, it is frequency shifting of the entire spectrum. M of t is represented as m of f. It is simply m of f minus fc. Okay, so I have again two terms here, that is Ka AC by 2, m of f minus fc plus m of f minus fc. That's what I get. A frequency spectrum of m of f is shifted by minus fc and plus fc. Okay, so this is how I can write by applying the Fourier transform to the standard equation of AM. Now, if I represent this in the graphically, okay, the frequency versus the magnitude graph. Let us say this is the original message spectrum m of f, which is low pass. It's a triangular representation what we have taken over there, but for representing the frequency, the spectrum, I can also use something like this. A low pass representation, something like this. The low pass filter characteristic, you know, right? The low pass characteristic is something like this. This is on the positive side, this is on the negative side. So where I have used, say, this is 0 Hz, the highest frequency taken as W Hz. This is minus W. See, any shape we can use for representing the frequency spectrum. Either triangular shape or maybe rectangular shape, whichever shape. It's a low pass signal because the frequency extending from 20 Hz to 20 kHz for an audio band in the radio broadcasting. 20 Hz is almost equal to 0 Hz. So I start with the 0 Hz up to 20 kHz. The highest frequency is 20 kHz, which is a low pass. Here W is a low pass component. So what I can say is this is your original signal, message signal, m of f. Okay. After modulation, we actually get a band pass signal. It's a low pass signal, baseband signal. So after modulation, this is what I'll get. See. So what we have there over here is how to represent it. This is the equation. In the frequency domain, we have to represent that graphically like this, something like this, which is already done. So what we have is, we have a delta function at minus fc and we have a delta function at minus of minus fc, right? That means we should have a delta, this is equivalent to this delta function here, okay, which has a magnitude of AC by 2, delta of f minus fc, the first part. The second part is having the same amplitude of AC by 2, it's a delta function, delta of f minus fc, that is a delta of f plus fc. That's what I have, two delta functions. So two delta functions are represented. Now second part is having a amplitude of Ka AC by 2. Okay, we have a lower m of f minus fc plus m of f plus fc. That means this entire spectrum m of f is actually shifted by minus fc and plus fc. So minus fc this side, plus fc this side. Plus fc means it is minus of minus fc. So I have a fc somewhere here. Okay, centered at the fc, I have to draw the same spectrum. Just look at this same spectrum. That means this spectrum is shifted right by a frequency of fc. So this portion is equivalent to this portion here. This portion is equivalent to this portion. Okay, this is lower sideband, which is having a frequency which is less than fc. That is, it is subtracted by W Hertz, the highest frequency. This is fc plus W. Fine. This is the upper sideband. This is the lower sideband. This is on the positive side. This is on the negative side. Okay, that is m of f minus fc is represented something like this. M of f plus fc is represented something like this. Now, if I calculate the bandwidth, what is required for AM from the frequency spectrum? How do you calculate the bandwidth? It is nothing but it is the highest frequency minus the lowest frequency. That is fc plus W minus of fc minus W. What we get? We get a bandwidth, transmission bandwidth of AM as 2W Hertz. Twice the highest frequency in the message spectrum. If I consider the highest frequency of say 10 kHz, the bandwidth required is 20 kHz. But in the normal AM broadcasting, say AM medium wave transmission, the highest in the audio band itself, that is 20 Hz to 20 kHz, we don't consider that the entire spectrum there, message spectrum there, for a transmission bandwidth allocation purpose for each stations, say Bangalore station, Delhi station or whatever. The highest frequency considered or assumed as 5 kilohertz. The highest frequency taken as 5 kilohertz. The highest frequency is considered as 5 kilohertz in the range of 20 hertz to 20 kilohertz. If the highest frequency taken as 5 kilohertz, in that case the bandwidth required is how much? The bandwidth required is 10 kilohertz. That is the TRI or whatever, these spectrum allocation agencies, they allocate just 10 kilohertz of bandwidth for AM medium wave transmission. This is the standard bandwidth allocated for AM transmission. Now, coming to the summary, what it all we discussed actually in this video is what is AM, changing the amplitude of the carrier signal proportional to the amplitude of the message signal. How do you represent the equation in the time domain? How to represent in the frequency domain both graphically as well as by using an equation. Then the bandwidth required for AM transmission. The standard is 10 kilohertz. Fine. So I hope you have understood whatever now we have discussed in this video. I thank you for watching this video.